This evening's paper title is Improving Cooling and Oil Distribution in Oil-Injected Screw Compressor. The paper is presented by Nasheen Basha. She is the winner of the Iowa Ted Perry Research Award 2021. Nasheen Basha is a chartered engineer and project manager for a research program aimed at advanced machine learning and computational fluid dynamics at Imperial Chemical Engineering Department. She has a very keen interest in fluid dynamics, multi-phase flow, computing, and improving diversity engineering. She graduated with a PhD from the University of London, focusing on computational fluid dynamics, modeling, and oil injection screw compressors. Over to Nasheen.
Right. Thank you for giving me this opportunity to do a presentation on my PhD research work, which is basically modeling of twin screw compressors to improve their efficiency. And yeah, so I couldn't start my work without thanking my supervisors and collaborators who have been a massive help for the work that has been done during the research program. In getting through the context, but the most important part of my PhD work today, which is obviously the part which has been presented in the paper, that's distribution of oil, how that would affect the temperature distribution as well as the compressor performance itself. But also there's another interesting bit, which also was a part of my research, that looks into breakup of oil droplets and various regimes of oil that would exist within the compression chamber. Then obviously I would lead on to the conclusions and go on to the future work, the possible future work for this research. Right. I think most of the participants here, I think we have a good number of attendees today, would know maybe more about twin screw compressors than me. But for others, I just wanted to show here how twin screw compressor would fit in the grand scheme of compressor chart diagram. So they are machines with two shafts where pressure is produced by change in volume. So what we have basically is wherever we need lower pressure, if we need a range of flow rates, then a screw compressor is the choice compared to other types of machine. So this diagram here shows simple techniques with screw machines where you have a simple process where there are rotors, and then you have male and female rotor. Gas goes in, gets compressed, and then comes out of the machine. And that's very much shown in this P alpha, which is pressure versus male rotor angle diagram. Right. Okay, so on to the next slide. So what is the motivation behind the research, that why I'm doing what I want to do? And that's because we know that the compressors consume a huge amount of industrial energy. And in the next few years, at least until 2050, according to the chart here, this is expected to increase substantially. So therefore, that would emit a whole lot of emissions into the atmosphere. In order to reduce these emissions, we have to make these machines more efficient. And here our focus is on oil-injected compressors because they are a huge proportion of twin screw machines. And oil in these machines is very important for cooling, sealing, as well as lubrication. However, if we have the excess amount of oil, that would add to the losses within these machines. Therefore, what we want to do is optimize the machine. So with the low amount of oil possible, we get very good efficiency with the compressors. So looking at the previous study, there are a few oil injection parameters that have been very important, and that's oil flow rate, oil droplet size, oil injection port, as well as injection temperatures. So, but however, if you look through various analytical models, they might be insensitive because if you maintain the same oil flow rate, but if you change the oil injection port position or number of oil injection ports, that wouldn't change, that would show a change in compressor performance essentially. Therefore, we need to look into some sort of computational techniques that will help us understand how oil is interacting with gas within this compression chambers and how the temperature distribution, oil distribution takes place. And also, even with experiments, this is hard to look into because obviously we would need a huge optical access to understand how oil is being distributed with high imaging techniques. Therefore, in this case, we look into computational fluid dynamics and modeling twin screw compressor with it. So that brings us to how we develop the computational model itself. So before we jump into the computational model that's for an industrial compressor, we had to do a whole lot of integration with the external grids with the Fluent solver. If you're doing CFD, obviously you would know that the grids are quite complex part of CFD. And for twin screw compressor, they are much more complex because first of all, they are rotating and then there are very thin leakage curves. For example, the industrial compressor that we have here, there is a very thin clearance gap of 50 micron. So doing a mesh for that, it's quite intense and quite complex. We have this mesh developed from in-house package developed within City University of London. But what we did in the study, what I did in the study was integrate this complex mesh with an ANSYS Fluent solver. So for that purpose, we had to understand the mesh positions, node positions in this mesh, and to match that node positions with the mesh in ANSYS Fluent and make sure that with the compressor rotation with time, the mesh nodes are being translated. So that's something which is there in my next slide. So, but I won't go through the complete details of this process, but this has been made sure that we do it in a parallel mode, because obviously these computational models are very time intensive and computationally intensive models. So we have to solve them on parallel computer cores. So this process, which is called as user-defined nodal displacement process, which matches the nodes between the mesh and translate the mesh with time according to the rotor rotation. All this was done on a parallel framework, so we can easily use that with ANSYS Fluent. So more details about the whole code and how it was developed is available in this publication. So anyway, so we have this industrial compressor that has lots of bearings, seals, and plugs. So we've simplified that into a computational model, which has a rotating domain and a stationary domain. And we have this mesh, which is for both for rotating and stationary domain. And then there are a huge number of numerical settings, computational models, solution settings, convergence criteria. I think most of it also is available in one of the journal from this. I think this is not completely visible, but it's there in one of my applied thermal engineering journal as well as my thesis. So I'm not going to go into a lot of details about how this model was set up. So yeah, so I can share the link later on if anyone's interested. Anyway, so we had this computational model successfully set up. And also we have to remember here that the interaction between gas and oil is a two-phase flow. So we had to run through 3 different multi-phase flow models. And from those 3 different multi-phase flow models, we found out that VOF is the suitable model because of its less solution time as well as the accuracy that it gives compared to Eulerian, and mixture model. So the VF model as well is chosen, and we have a publication as well based on that, which I can also share later if needed, right? So this is the compressor that's in test rig. You can see that the injection is on the female rotor side, and this is a very standard sort of injection for an industrial compressor. So we designed a compressor of different sizes for all of them. We obviously had the injection port on the female side, and this is one injection port, and that's a standard compressor design. So here in this, obviously we are going to look into if that's a good design. Yeah, and for that purpose, obviously we have this compressor in a test rig. This P&I diagram, I think, is very much self-explanatory for most of you here. We basically measure the pressure, temperature, and torque, as well as the compressor RPM, and we put them into equations so we can obtain an integral performance of power, power, flow rate, as well as specific power. And we know the specific power is quite important in order to assess the performance of these machines, which is simply power by flow rate. Right, moving on, quickly getting to some of the results. So what we would like to understand here is how changes in oil mass flow rate will affect compressor performance, will affect the oil distribution. So for this purpose, what we do is we go on with different oil injection ports. So starting from 3 mil, 4 mil, this is 5 mil, and this is 8 mil oil injection port. So what you see here is the oil being injected on the female rotor side. So when oil is being injected on the female rotor side, the oil volume fraction, that is the region in red, is it is very it covers a whole lot of female rotor surface, and that remains same for various oil injection diameters. For 8 mil, you see a whole lot of rotor surface is being covered by oil. But however, what you see here is that even with different oil injection port diameters, the distribution of oil, the volume fraction of oil on the male rotor surface remains sparse, and that is still there even we change the oil injection diameter from 3 mil to 8 mil. Even at 8 mil, the distribution of oil on the male rotor surface is sparse. And this is further seen by plotting oil volume fraction versus the percentage of rotor surface area for male rotor and for the female rotor. For male rotor, you see the less amount of surface area is wetted with oil compared to female rotor surface, which is 1.6 times higher. So let's see how temperature looks like.